So this is still analytic description. At this point, I looked at the Floer lecture, Salomon's Floer lecture notes, and I have to admit that there's really not a whole lot of details on the gluing. Right? So what I'm going to say today, if at all, is in McDuff-Salomon. And honestly, my source is my own paper on the instanton Floer homology. That's where I learned how to do, gluing in full glorious detail. I think Matthias Schwarz's thesis probably has that in the holomorphic curve case, which I should actually put it. Probably on the literature list. Quick recap here. There. Right, so to make my life easy, I was talking about gluing just in the case where I'm assuming transversality and I'm assuming index 0. So, well, index in the sense of virtual dimension, or expected dimension, 0. So in this case, we're looking at two pseudoholomorphic cylinders, right? There's a perturbation by a Hamiltonian in the picture that limit to the same periodic orbit at different ends. We know that that also comes with an exponential decay estimate. And when I say that this is somehow an isolated broken one, or broken trajectory, well, isolated and transverse, I guess. What I mean is that the linearized operator for both of them is surjective and has only one-dimensional kernel that comes directly from the R action by shifts. Right? So that means we have a situation. Think of a broken guy, and now would like to find unbroken trajectories nearby. And for that purpose, we first do this pre-gluing construction. Which, takes these trajectories near their non-common ends pretty much, does exactly the same thing, and then interpolates. And here I didn't quite give you the entire interpolation, right? So there's a bunch of choices here. This interpolation here actually sits at the critical, at the periodic orbit in the middle for quite a while. And it just gets there, so there's some interpolation on an interval of length 1 from U minus to that periodic orbit, and another interpolation from U plus to that orbit. Right, so that's almost holomorphic. And then the trick is to find a nearby actual holomorphic curve, and for that purpose we run a Newton iteration with this function here that takes tangent vectors to this pre-glued curve in the space of all maps, and pushes the pre-glued curve with the exponential map in that direction, and then tries to solve d bar equal to 0. We'd like this to be a map between Banach spaces, so there needs to be some parallel transport back, actually, inverse here. So, good. All right. So then here's the bold claim that I used last time to argue that we do have unique solutions. So A says that the d bar for large R is actually very small. So this essentially says that we almost have a solution. B is an estimate in terms of the linearized operator at 0. It's an estimate that looks as if that operator was sort of invertible, certainly injective, but it's restricted to some subset. So this is something like a right inverse. And the last one is, well, it's a quadratic estimate, and it's a little bit nicer than even saying that this function here is actually C1. But that's essentially the context or the content of these claims. And the key is really that all these estimates hold for all sufficiently large R with the same constants. So that then allowed me to run this Newton iteration, and I got a very explicit constant here, so that when R is bigger than this, the estimates that I get from here sort of fit into the conditions of the Newton iteration, which give me a unique solution. So there's a unique one. X's and zetas are all the sections of the pullback tangent bundle, and now the unique one that I'm finding is in this space here on which I have the right inverse. So I'm asking it to lie in there. I'm also asking it to have fairly small norm. The delta is another uniform constant here. And I'd like it to actually be a solution. So the statement is that for this estimate, that's a unique solution, but then once I have that unique solution, it actually satisfies a better estimate in terms of the right-hand side of A. So the actual error that I need to make up for in order to get my curve to be holomorphic again actually goes to 0 exponentially also. Yes?
So does delta have to relate to C0, C1, C2?
This capital delta? No. Yeah. No. That just comes essentially from the size of the domain on which I can define FR. Yes. Right. So this is not quite honest here. I can't really define the exponential map applied to any C. I'd like it to be C0 small. All right. So really, I should take here C less than delta. So that is just the size of the domain on which I can define that. Yeah. But again, right, it needs to be independent of R. So that delta. That's the game here. All right. Other confusions tends to get grounded. Yes.
I have one on the gluing map, but maybe you haven't gotten there.
Yeah.
So.
Okay. Right. So, I should now. So once I have these unique solutions, I define the gluing map by saying, well, really, I would just like to map R here to X to my honest holomorphic curve. Right? So that doesn't just depend on R. If I have, look at the whole set of connecting trajectories or broken trajectories here, I might have different pairs U minus and U plus. Right, so they give me different pre-glued maps. And then this is also not quite true. Well, so for several reasons it's not quite true. So this is the one, what I would do for R less than infinity. for gluing parameter equal to infinity, I want to get into this compact space, I would take the unglued sort of pair. That's what I think of as the broken one.
Yeah, so that was precisely my confusion. So I just want to double check that this, in particular, you're kind of getting like a neighborhood of the boundary.
Right, exactly, yeah.
And
that's the idea here.
The question was, though, to understand the boundary, however, do I need to know this map, the full map, or do I just need to know the gluing map at infinity?
Well,
like, I mean, this is
well,
nice.
I mean, the gluing map at infinity is trivial here, right? There's sort of, well, so first of all, okay, so let me.
Well, it says that.
Yeah, let's get back to that in a second. Let me first say, so this is also not quite it, because all of these moduli spaces are modulo R shifts. So I'm going to need to say really, honestly, these should be maps from equivalence classes to equivalence classes. And so one of the questions we're going to need to ask is to what extent that's well defined. Okay, but let's see. So the question was, do I need to know my gluing map? So what is this good for, actually, right? Why do I need the gluing map for finite gluing parameters? So one answer is, well, I want to give this guy here the structure of a manifold with boundary, right? And so in order to do that, I need to make a homeomorphism to a neighborhood of a boundary point. And so that's the boundary point here, and the neighborhood is given by the actually glued curves. So, in other words, if you just look at this gluing map at gluing parameter infinity, of course you're identifying the boundary with, you're identifying the broken curves in here with pairs, but you're not saying how the two are connected, right? The unbroken curves and the broken curves. Right, so this here, right, M bar is something like right, actually holomorphic ones, mod R, union broken curves. But if I write it like this, it's sort of a disjoint union of sets.
Sure.
It doesn't even have a topology that makes it connected. And so I give it a connected topology by using the gluing map to say what a neighborhood of these broken ones are.
Isn't the thing you're doing giving it a smooth structure, and you can get
right.
topology just from growth compactness?
No, we got the topology from the pre-gluing map. Right, so Gromov compact. Well, there's a Gromov topology, right, which uses the pre-gluing map, or some other notion of shifting things apart and converging.
I thought that McDuff-Solomon defined the Gromov topology without any reference to gluing.
Right. Yeah, you can. Yeah, but I mean, but you still have to parameterize different parts differently. And to me, that's sort of half of the gluing map. It's just sort of, put things together in different parameterizations. You can just, you can define the Gromov topology by forgetting about the area near the node, because it's sort of canonical, or sort of natural what happens there when you know the rest. Or you could write down your pre-gluing map to capture that.
So with regards to the gluing map being between equivalence classes, we use a local slice to pick these out? Is that?
Well, okay. So, so here's that gluing map again, and so question number one is, right, how's that well defined, and is that even continuous, right? Because in order to give that a smooth structure, it should be a homeomorphism. So homeomorphism means continuous injective locally surjective. So let me actually first, let me mumble something just in terms about the well-definedness, and then we'll talk about the continuity here. So in this case, right, these are all finite sets. And so what I could do, just to make my life easier, I can make this thing well-defined by picking a representative in each of these. By picking a representative of every point in these, right? That is easy because all points in these moduli spaces are isolated, so I don't need to worry about continuity of that choice. Right, so strictly speaking, I should sort of write orbits as something that doesn't know about a representative, so this curly U is an element in one of these M zeros. And by picking a representative, I mean, finding an element in that orbit or writing curly U as the equivalence class given by U. So if I do that, then this map is perfectly well defined because I have the representatives, I do whatever construction I do with it, and then it's okay to take the equivalence class afterwards. That's the direction in which that ambiguity is not a problem, because you're projecting down. So, won't worry about that one. We'll worry about injectivity and everything. Let's see. So, let me try to get... Oh, no. No, injectivity... Sorry. Injectivity, I think, as a statement is perfectly clear, right? So I would like this entire map from the union of all these pairs and all these intervals to be injective. When I say locally surjective, and let me say what continuous means here. Well, continuity for finite gluing parameters is fairly clear, but in particular I want continuity as R goes to infinity. So that's the one that I'm going to try to say how that works. So if I fix U minus and U plus, and I let R go to infinity, then I would like the preglued curves, or the preglued and corrected curves, to actually converge to the broken one in the topology that we gave before. I'll write that topology down again. Oh God. Right. So that's the continuity. Injectivity is fairly self-explanatory. And then local surjectivity is saying that not only do I have these sequences of glued curves converging to the broken one, but there are no other curves close to the broken one than the ones that I get from the gluing map. So the claim is that for every broken one, there's a neighborhood of it in the moduli space. So this is a neighborhood of the broken curve. So that any point in that neighborhood, so any equivalence class of curves, is in the image of the gluing map right. So if I have a point in that neighborhood, then there is a gluing parameter so that that point is given by the gluing map. In terms of actual maps, that's a little more complicated, right? Because I have shifts here. So really I'm allowing myself some shift here off. You know, if I give myself a map V, I'm allowing to shift that. And after that, it should be equal to map, the actual map from which I got this gluing map. Right, so we'll,
and I can always pick V to come from U minus and U plus in particular, because that's how you define the neighborhoods in the broken curve. Is that?
V is in this neighborhood of U minus and U plus.
And neighborhoods of U minus U plus are always of that. Come from U minus and U plus.
That's what we're trying to show.
Oh, okay.
Right, so there's a notion of neighborhoods of broken ones, and the claim here is that every broken one has a small neighborhood.
Okay.
Right, so the game is, you give me U minus U plus, I then find a very small neighborhood of U minus U plus. Right, so this V essentially knows that it's very close to that broken one and not any other broken one. Right, I'm gonna make that choice so small. Right, so right, so the choice of neighborhoods tells me which U minus U plus this is, and so then the harder game to play here is that from this map and the broken one, I need to find which gluing parameter I need, and I also need to find which shift. So
you actually intend to define the topology on your moduli space before you define this map, otherwise what would you?
Sure, and we did that a while back using, I said what Gromov convergence meant. I also sort of wrote.
No, right. You said that the pre-gluing map was given the
can
topology.
Give you a topology, right? And you don't, as Nate points out, we don't actually even need the pre-gluing map to make the topology.
And this gives the differential structure also.
Right, then, rho here gives you a local homeo, so that gives you a differentiable structure.
So just want to double check.
Yeah.
I don't. Even without using this full gluing map to get the neighborhood, it's like I still know that this moduli space has boundary.
Well, how do you know what do you mean by boundary?
Okay, so I guess that
Right.
that is therefore my question. Like,
Yeah.
is there a way for you to understand that this moduli space has a boundary without using
Giving a chart as a manifold with boundary? I don't know. I mean, people
So you can't get away
talk
with just
that way all the time. Yeah.
So you can't get away with just the pre-gluing method.
No, I wouldn't know how. How do you say that a point is in the boundary of a space unless you give that space a structure? That.
So if on number 2, I guess you don't have that. We could have this if we haven't proved number local search activity.
Right. Yeah. Right. If you have a cusp. Right. Right. If your M bar could look like this, and there could be could think of a broken one being approached by sort of two branches of not broken ones. Right, so this would be bar 1. There could be a gluing map that just gives me part of one of the branches. right? But what fails here is the local surjectivity, because if I take a whole neighborhood, there's other points on the lower branch that are not hit by the gluing map. And in fact, this very much does not look like anything with boundary. Or maybe, but it's not clear whether you should, so there's the question here is how should you regularize it? There's various ways in which you could think of regularizing it. Maybe it's just a smooth piece. Maybe it's supposed to be a cusp, which is not really terribly regular. Or maybe you're supposed to separate this into two things. So without making the gluing map, you don't know what the right sort of nice representative is. And just topology, I mean, there's sort of drastic differences here, right? Even just in terms of algebra, here you'd have two contributions from a boundary, here you'd have no contribution, and here you'd have funky contribution. Right? So, and that's a very local choice, right? The rest of your moduli space might look the same, and so you really need sort of only one answer here of what the structure should be. Yeah, and I mean, it's, we like to sort of write down these sort of compactified moduli spaces and say that, well, the broken curves are the boundary.
Doesn't Gromov compactness tell you that?
No, Gromov compactness tells you that it's a compact topological space. Right? Topological spaces have no boundary. There's no notion of boundary in a topological space by itself, unless that set sits in a larger set. Right? But our Gromov compactified moduli spaces don't sit in a larger ambient space. So, yeah.
Okay, that was my whole confusion.
Yeah.
I assumed, I always look at a sequence of curves, and then a Gromov compactness is going to limit something, and I would always assume that that's going to be my boundary
You
point.
want that to be the boundary point eventually, right? But you need to make it a boundary point. And also, if you think about sphere bubbling, your first instinct might be to say that nodal curve should be boundary in some sense. But it actually turns out that spheres are supposed to really just, sphere bubbles are, if you put them in their right place, really they want to be just interior points of the moduli space. Maybe interior points near which the smooth structure isn't terribly nice, but certainly sort of codimension 2 points that don't contribute to a boundary. So, right, and this, there's a whole industry of sort of philosophy of what these things ought to be, and the only way to make these philosophies rigorous is to construct these gluing maps, fully, as local homeos.
Philosophy of what ought to be?
This whole sphere bubbles are supposed to be codimension 2, disk bubbles codimension 1, figure 8 bubbles codimension 0. So, you can sort of mumble that, and you can talk about Fredholm indices, but that's all sort of expected, right? And in order to really make it true, you need to give it that structure. Right, the other, since we're at that place, there's another example that's good to keep in mind in terms of corners. So these two bits here of moduli space are actually locally homeomorphic. Right, there's continuous map that has a continuous inverse, right? Yet, the natural, as I've drawn it as subsets of R2, this has a smooth structure as a corner, and this has a smooth structure. It's just, simple boundary point. And so we really need to talk about smooth structure rather than sort of topological manifold in order to really honestly be able to talk about corners. So that's okay. So I guess in terms of the gluing map, the statement of Gromov compactness sort of now becomes easier. I don't have to, I don't have to sort of, of course we used Gromov compactness somehow to define the topology in which all of this made sense. But let's say that gluing map is here. So then I can talk about this one-dimensional space. Oh, I should take actually all gammas. Oh no, hold on, sorry. Right, I fixed gamma minus and gamma plus. So I could take this, what we'd like to be the compacted, right? We would like this to be a one manifold with boundary. We could say that in terms of the gluing map, but we could also say that if I take this and take out the image of the gluing map, right, then I would like to say that this is compact, and this is now simply a subset of parametrized maps mod R. So I can think of these as maps from R times S1 to M mod R. That's a known entity as a topological space, and the claim is that that's compact. So I think we said that before. I could give this full moduli space the structure of a manifold with boundary and corners, or I could cut the ends off and then actually get a submanifold with boundary of this space, which however is not really a manifold in any sense I know of. So it just has a topology.
Would you remind me why we want to say that this thing is compact rather than all of M bar?
It's just harder to say that all of M bar is compact because then I have to refer back to the Gromov topology. So this is another expression of Gromov compactness here, which just uses this W1P mod R topology. So just many ways of saying the same things. Okay. Good. So let's see. So I've mumbled about fixing representations to make the gluing map well defined. So now I should argue about continuity. Let's see. So, and there's different places, right? So continuity at finite R, I would have to argue that there's continuity in the Newton methods. For example, I should have continuity of not just FR, but probably its derivatives with respect to R. We'll get there. We'll need that at a later point again anyways. At R equal to infinity, right, this is the weird thing. For R finite, I get my solution from the Newton iteration, and for R infinite, I do nothing. So there I really need to compare Newton method to something else. So but what do I have here? I would like to know that X WR of zeta R converges to the preglued one. Right, so I can prove this by, fixing an epsilon neighborhood of the broken one, and now I need to, find an R so that for R sufficiently large, this guy lies in there. Okay. So I should make sure what. Right, and this is right. So I guess I've given many different definitions of the Gromov topology at this point, and I think this is yet another one. They're essentially all the same. The one thing that I did say at some point in response to a question was that I wanted some sort of topology with exponential decay, and that is just utterly unnecessary. So certainly once these guys are holomorphic, so this V here is a holomorphic curve, I don't need it to have exponential decay to the right places as long as it's C0 close to something that converges to the right orbits. So what I need here is, right, I need a representative in here, so I need, I could take some shift of this, but in particular I could take straight on this representative that we constructed. And that's supposed to be close to the preglued curve, but that preglued curve is nothing else but the WR that we had. So pretty much what this estimate here says is that I just like to get zeta R in W1P less than epsilon. And we know that we get that because these go actually to 0 exponentially with R going to infinity. So that's pretty much how the whole method was made, right? So we go towards the broken curves at R equal to infinity. So it's just reality check that is indeed pans out. So injectivity you could go at this in various ways. Let me just sort of start with the dumb first idea and then see what remains to be done after we get out of that. So if you want to prove it's injective, let's assume it's not injective, so let's assume we have. I'm going to drop the equivalence classes here. I'm going to assume that I've fixed all my representatives, so gluing possibly different broken curve, possibly different gluing parameters R and S. What if I get the same point? And one thing I'm allowed to achieve injectivity is to take my gluing parameters very large. So I'm going to, by contradiction, assume that I actually have sequences going to infinity, so that for different gluing parameters I get the same thing, right? Hold on, right, sorry, they don't necessarily need to be the same. They don't necessarily need to be different. So there could be two ways in which injectivity here fails. The gluing parameters could not be the same, or even the broken curves could not be the same. the reason I'm allowed to fix the broken curves in this sequence is that there's only finitely many of them. So I've already taken a subsequence right, for which this is, I get all this. So yeah.
So if I assume that I don't have injectivity, how do I get a sequence like this?
I'm assuming that I don't have injectivity for any large R. So what this follows from rho on R bigger R1, not injective for all R1. Right. So if it's not injective, however big my R1 is, then I find these bigger than R1, and I'm going to find, broken trajectories, that will give me this equality, and then I can take a subsequence in which the broken trajectories are at least constant, right? They might be the same or different. So the goal now is to prove that for some large I, you actually need to have u minus equal to v minus, u plus equal to v plus, and Ri on the nose equal to Si. So that would contradict the assumption of not having injectivity. So, all right, how do we get that? Let's write this out here. So the exponential at the pre-gluing on some Ri on some zeta Ri is equal to exponential of the other pre-gluing some other error that makes it holomorphic, but then I have equality mod R, so this might also have to get shifted by some yet another parameter. So right. But that means that, well, so zeta and eta are both pretty small in C0, certainly. Right? So this tells me that, well, so some C0 distances are small. One is the C0 distance, well, between the preglued curves, but the preglued curves are equal to u minus or v minus on certain intervals. So u minus, let's say on, what was that, dot plus r I dot is close to v minus, that gets shifted some other way. It gets shifted by the SI and then the TI. So this is forced to go to 0 when I should be somewhat careful with C0 is not on all of R, but maybe on from minus infinity up to some quantity that you get from RST, which, however, we can convince ourselves, no, that might not go to infinity because I have no idea what that t is, right? Right, another lesson, and you should really anally write out your complete and utter complete proof, because there might be non-trivial little subtleties involved here. So let's see. what else we get here. So u minus on some intervals gets very small, and I get the same thing for u plus, just shifted in another direction, close to v plus, and that will be on an interval that somehow has to do with that same constant SRTI up to infinity. And I would then like to argue that that at least means that, you know, either for the minus pair of or the plus pair, this means that they actually have to be the same up to shift. But I recognize that there is a bit of a gap. This is also, right, the areas in which these guys are really precisely equal to the preglued ones are separated by width r, or respectively s. And so, you know, this is not exactly the same number here. Sort of the minus version, and that's the plus version. We probably need to take into account that we also know that each of these guys actually exponentially decays towards some periodic orbit. So.
You still want to hear the argument that GI is finite?
Yes.
Okay, here's what you do. Okay, so consider the intermediate orbit. I don't know what you
That
call
these
that.
two have, right, so this might be gamma, so this might break at gamma, and this might break at delta, right?
Yes, and I think that neither gamma nor delta can be the thing that u plus and v plus are tending to at infinity, right?
Why? I mean, u minus could be a self-connecting trajectory, right? From gamma minus to gamma minus. Yeah, it's not supposed to have it's supposed to have non-zero energy. So, yeah.
Okay. Well, if we can have self-connecting trajectories.
Right. Yeah. So this, right. Okay. I owe you clean up of this.
Can we just say they have the same broken trajectory limit?
Well, that's what I'm trying to argue here.
But you assuming you have a sequence that they are the same.
That the preglued ones are the same. Yes. Oh, right. Oh, that is excellent. That is utterly silly. Good. Awesome. Okay. Perfect. I can take the great big eraser. Indeed. So these guys here, right? Well, hopefully. So this is assuming point number 2, I think. Right, so in 2, we're claiming that as I goes to infinity, this is going to converge in the Gromov topology to the pair u minus u plus. And this here is going to converge. Right, since Si also goes to infinity to the pair v minus v plus. And since limits are unique in my topology, right, this means that this has to be the same. So let me say this is because the Gromov topology is Hausdorff. Yes.
Wait, but I guess, okay, so this kind of goes back to my other question, which I think is slightly different than what I actually said. But when we defined those neighborhoods with the pre-gluing map, did all of the things in a neighborhood of something which is pre-glued, do they have to use the same, like we could have different limits coming from different directions with different like limiting pre-glued things, right?
Hold on. So we're just
Yeah, is that
thinking
an issue?
we're just thinking about like the case where broken things are isolated.
Oh, okay.
Right, so that's the only, yeah, I
Okay.
mean, but if you have larger moduli spaces of broken things, there's more things to worry about here.
Okay.
Right, so I'm always, so when I talk about a neighborhood of a broken trajectory here, I think that my broken trajectory is actually in just an isolated point, and so that neighborhood will not intersect any other broken ones.
Why do we not need to take sequences of maps ui plus ui minus?
Oh, because there's only finitely many of them,
Oh.
so I can take a subsequence.
So we're not proving injectivity where sort of the ui or u plus u minus, all these things live in sort of in positive dimensional moduli spaces.
We're not doing that right now. No. If you wanted to do that, obviously you'd have to sweat some more, right? Yeah. So, well, if you wanted to do that, you'd already see here that at least these guys here for finite I will have to be near each other. Yeah. Okay. So, on some level, this is a little unsatisfactory because I have not proven that the Gromov topology is Hausdorff, right? But, well, if you look at the definition of so now you'd have to again go into the definition of this topology and check that really tells you that the limits need to be the same. Right. And so now also, so the equivalence classes are the same, but we fixed representatives, right? So that means the actual maps are the same. So what, however, isn't clear yet, right, is whether the gluing parameters have to be the same. And so for that, we actually do need to look at the equation again. So I can actually just talk about WRI and SI, I guess. But again, I have this pesky possible shift here.
Why there is this shift? When you show that the actual curves are the same, doesn't tell you that.
Oh, because the equality is always in the moduli space, right? And the moduli space is mod R.
Okay.
Right. So, right. And so I can look at this, say, on some intervals of no. Right. These extra TIs are a gigantic mess. So, right. So the WRIs here are, close to U minus shifted on certain intervals, and so this whole thing is also close to U minus shifted on another certain interval. So both of these intervals have some intersection. And I know that U minus cannot be periodic, because otherwise it would have infinite energy. And it not being periodic means it's also not allowed to be close to periodic. And so that means these two shifts here actually need to be very close to each other. So if they were far apart, then U minus would be sort of close to periodic. So, right, so turning this into actual estimates is a little more dicey, but this is the basic idea here. So this then tells me that Ri should be close to this shift Si plus Ti. But then I do the same thing with U plus. And for U plus, the shift works a little differently because there's a minus sign here and on the Si, but not on the Ti. So that's going to tell me that Ri is also close to Si minus Ti. And so together that tells me that Ti is actually bounded and close to 0. And the R's need to be close to the S's. So I get some sort of injectivity away from very close to the diagonal. And, just like with all maps from a continuous domain, you can't sort of prove by discrete methods that it's going to be injective in some infinitesimal neighborhood. So what remains to prove is that prove local injectivity. Question. Let me state local injectivity. So if R is not equal to S, but R is close to S, then gluing should be not equal to S. Fixing U plus and U minus here. And that looks like something that sort of begs to be proven by a derivative being non-zero. So if I could prove that my gluing map actually has a well-defined derivative, and that's non-zero, then I get in some epsilon neighborhood that the map does change. So, but what can I say? Well, so there's more hand waving here. Of course, there's the Newton iteration in the way, but I would like to say that the derivative of this one is close to the derivative of the glued map. What that essentially says is that in the Newton iteration, I have not just the errors or the changes that I need to make to keep things holomorphic are small, but also their derivatives need to be small. Which I can prove by looking at what equations that satisfies. Hopefully, and we'll possibly get there. So if we have that, then I can look at what this pre-glue thing does. And on some large domain that's equal to shifts of u minus, but I'm taking an R derivative, so the shifts actually get me a ds out. And then there's some interpolation going on, and in some other domain I get ds of u plus from shifting in the other direction with R. And so I have this equality on pretty large domains where u minus and u plus are most definitely not constant. So this, either of these parts is just simply not equal to 0. So they have some significant energy on those bits. Because I really only interpolated and cut off in the area where u minus and u plus are very close to that intermediate periodic orbit. Right? So pretty much all of their energy is captured here, and that's very non-zero. So that gives me some space here. I can make some significant errors in this approximation, because this is pretty non-zero. Yeah, this is maybe the most sort of obscure part of this proof of how one does that. So let me try to write the derivative of the gluing map down for real. So I should take a derivative of the exponential map. And now I'm going to write the exponential map with two entries. Right, it's a map from a pair of, a base point and a tangent vector. So we call this sort of the first entry, and that's the second. Because then I need that so I can write down the chain rule. Right? So I need to take the derivative of the exponential map by the first entry at w zeta in the direction of dr w, and then derivative by the second entry in the direction of dr zeta. So I know that zeta is very close to 0. And then I know something about the exponential map just as a map from like a single point and tangent vector. Is that if I chuck in 0 here, these derivatives actually are the identities. So this whole thing is about the identity. And that is also about the identity. Another way of understanding this is to think that this whole thing really is pretty much, right, in some local coordinates, what the exponential map is nothing but WR plus zeta R. So that was just a way of formalizing that. Okay. This is the term that I want. So I'm good with that. This is the term that I want to get small. So in order to estimate that, I'm going to write down the equation that it satisfies, namely FR of zeta R is equal to 0. So that is my key, and I can take a derivative of that. So then again, we have various derivatives in the picture. So on the one hand, I can take the derivative in the direction of these tangent vectors, zetas. So we call that a capital D. So this is where I fix R, take the derivative as a map, and then apply that to dr. theta r. But on the other hand, the maps also vary with r, so yeah, I have to take the partial derivative of f in that direction. This being 0 means I can throw that on the other side. I get a dr fr. So this side is the not so interesting one. If you write this out, your fr of zeta r are d-bar operators. They're all pretty small, and you then take r derivatives of something that's pretty small, and that tends to not change that much either. So if you write this out, it's not so hard to convince yourself that that's pretty close to, or that goes to 0 as r goes to infinity. The more interesting thing is this side, because right, I want this guy to be small, but what it gets multiplied with is some operator that might not be invertible. So I need to check out what's going on with the kernel here. So what this is essentially just the d-bar operator on stuff. So this is the linearized operator at u minus on some large part of the domain, and also linearized operator of u plus on some other large part. And so that has kernel. So I need to somehow convince myself that this variation is transverse to the kernel. But the nice thing is that I know that my unique solutions here, the zeta r's, were given in the they were given in the, well, we called them QRs. Well, QR was this right inverse, so that was a complement to the kernels. At least dr, where dr is the linearized operator of the bar at wr. So this here is not quite the same as that operator, but I think that's essentially the reasoning here. So that can get written out in more glorious detail, and I'll probably do that on the notes. But so that's the idea here. So
the idea for what?
This is the idea, right? So this gets small, and these elements here sort of want to lie in complements to the kernel of this guy, and so then that tells me that drfr also goes to 0. Oh, sorry, dr zeta r. Which was the remaining part that I needed to get the derivative of my gluing similar or close to the derivative of the pre-gluing, right? And that was the one that I knew was very non-zero.
Why is this very non-zero? I mean, why not close to 0 with r also?
Well, that's because we know what it is. Right, it's the ds derivative of u minus, and that's on a large domain on which essentially the whole energy of u minus sits. So okay, so I have now successfully waved my hands about.
Wait, can we go back to the latest
Yep.
slide?
It's just continuity and injectivity. So local surjectivity might still have to happen.
So this linearization is going to 0? Is our infinity?
Right, so the linearized operator on this, right, so there is a vector, this vector here I'd like to get small.
Correct.
Right? And from the equation that it satisfies, I know that some operators applied to it go to 0.
Okay.
But the operators have kernel, so I need to somehow make sure that these guys lie. And then this is a big gigantic lie here. Right. Okay. So let me say this is actually pretty fuzzy here.
This is kind of like squeezing. You're like putting a function applied to it, but it's never vanishing. But it's like a magnitude that's always going to 0 on its operator. I guess I just don't see why I could deduce that $0 goes to 0.
Well, because okay, so we do have an estimate that says zeta is less or equal to some constant d r zeta whenever zeta is in the image of the right inverse. So if I knew that not just the zeta r's are in the image of the right inverse, but their derivatives, right? So that's the fudging here. Question is, can I apply this to the r zeta r? Okay. So then I chuck this in here. Then I have this right-hand side going to 0, and that tells me that the left-hand side goes to 0.
Yeah.
Yeehaw! Okay, so I have successfully not proven the local subjectivity. So I guess yeah, why not? I'm just gonna spend some more time on this on Wednesday, because yeah, these are really things that are not so obvious in the literature. So I'll try to make precise the hand waving that I did, where that so then ingeniously replaced by Hausdorffness, and I'll also go at this subjectivity here, sort of right, preview being. Right, so this is my key equation here. Right, I'm giving a map V, and now I need to find, well, I know U minus and U plus, so I need to find shifts, knowing parameters, and zetas. The one thing that helps me is the uniqueness statement that I get from the Newton iteration. So the good news is the Newton uniqueness. Which says that if I have d bar of x w r of zeta equal to 0 and zeta lying in my image of my right inverse, and zeta being small, then zeta actually has to be equal to the unique solution that I had. So the goal that I'll have here is to find S and R so that I can write this V as X WR of some zeta, where zeta is in that given domain, right? Because then the Newton uniqueness is telling me that it actually is the zeta that we stick into the gluing map. So I don't really have to find the zeta at the end of the day. That's given to me by the Newton uniqueness, but I do have to find the S and the R. And that's another fun implicit function theorem. So there's many sort of smaller scale arguments that all kind of use the same transversality and knowing the kernel and knowing exponential decay. So the overall philosophy is that we know our settings, we know our estimates, and every new problem you kind of throw the same set of sort of finite set of knowledge at, and something is going to do the job for you. Hopefully. Right? Clearly it doesn't, that shouldn't save you from actually writing out the details. So I will exercise that on Wednesday.